All right, we are down to our last 2 weeks of class and we are just starting circuits. So unfortunately, we don't have time to cover everything there is about circuits. In fact, we'll only get really a small segment here, but we'll do as much as we can. And I would like to try to do as much of the notes out of class as possible in this so that you can play with circuits in class. That's the fun part. So this is just going to be a quick introduction to circuits, starting with a discussion about electric potential as it relates to circuits. As you know, we spent last chapter talking about electrostatics, and in electrostatics, they talk a lot about electric potential. So this is kind of the bridge between the last chapter and this chapter. So if you remember from before, we had the top of our electric hill, we said was the positive part. If this were two charged plates, which this is, then you have the top of the electric hill and the bottom of the electric hill. In the middle, you have an electric field caused by the difference between those two. So if you put a charge in the middle here, that electric field is going to go towards the negative plate. Again, that uses that definition of a positive test charge, so that is what determines the direction for electric field. So you can see how they kind of did the high and the low on this image to correspond to how it would be for gravity for something falling off of a cliff or something like that. So to the notes here, if you have, when we talk about a battery, what a battery does is it provides an area of high electric potential and an area of low electric potential, and that's what causes current to want to move through a circuit, is by having something with a battery in it. So let's see. So charge moving through, as you go through the circuit, you're going to have different changes in electric potential, and I'll explain that here as we go. So here's a real simple electric circuit, and we've started with this in class. This is kind of funny because this is a 12-volt battery, which is like your car battery with a light bulb. I don't know if that would really work well, but anyway, it's a nice picture. And but it does have a nice image for the electric field. So again, if I looked at the electric field, and if I were to put a positive test charge here inside the battery, it would go right to the negative end. And if I were to put a positive test charge along the wire, it would make it go along the circuit and eventually end up back here at D. So you do have electric fields throughout. You have the strongest electric field inside the battery because it's such a small distance, and as the distance increases, your electric field then, let's see, as you go, you have a lot more room to make that same drop in voltage than you do inside a small battery. So again, by the definition of electric field, the charge is going to move from the positive to the negative. So we continue that convention here. So we've already mentioned that the positive terminal is the high potential and the negative is a low potential. That's the way that works. So here we have a little graph, and I have a simple circuit set up on this picture. So we have a 1.5 volt battery. Most of the batteries that you use for electronics or toys or whatever are usually 1.5 volts. It doesn't matter whether it's a C battery, a D battery, a AAA battery, they're all 1.5 volts. It's actually the chemical reaction that's inside the battery that dictates the voltage of that battery. So it's not how large the battery is. If it's, say, a D cell, those really big guys, they just have more chemical in them than like a little AAA battery. So that's why they use like C and D batteries mostly in kids' toys, because they suck a lot of juice, so that the batteries would die really fast if they used little ones. And something like your remote control for your TV or something is usually a AAA or a AA battery. And the reason for that is because when you push the button, it doesn't take much electricity at all to send the signal to your TV. So here we have, anyway, one battery, and then we have two light bulbs set up in series. Series meaning there's only one path from positive to negative end of the battery, and we'll talk about series and parallel a little bit later. On this above, so this is the actual picture. Above you have the diagram for it, the circuit diagram, and with that, this symbol here means battery. The little part is always the negative end. Think about that as like the little knobby part on the battery, and then the other side is the positive end. So we're going to have current that's going to go to the right through, this would be a light bulb and this would be a light bulb, so through both light bulbs all the way back around until it reaches the negative end. So the question on this part is we're going to look at what changes in the electric potential as you go through the circuit. I sometimes have kids do this in lab, but honestly they don't really care for it, so it's probably just as well for you to see it here and look at what happens. So if I go from A to B, A being the negative and B being the positive. So if I can take an electron and I can bump it up to, well, I'm having the positive charge carrier, but if I'm going to put the charge carrier at the positive potential, then that's to the top of the electric hill. So I have a large increase in voltage if I go from A to B. Next week we'll play a little bit with multimeters, and you can check the voltage on batteries. That's actually a really handy thing to do whether you're in physics or just living life and wondering if your battery's dead or if your device is bad. A multimeter is a nice thing to do that with. So if you go from terminal to terminal in the battery, you should have a large increase in electric potential, and that corresponds to a strong electric field. As you look at the wires do have an electric potential, a change in electric potential, but it's very small. So I put that as just a small slope here. When I go then from C to D, I'm going across the light bulb. Across the light bulb there is going to be a voltage drop. So I'm going to have a little slope on that one. Again, D to E, I've got my wire, so not much change. E to F, another light bulb. It depends. If the light bulbs are the same, then you will have the same voltage drop across both of them. In this case, I made a different one just, for argument's sake. And then at the end is just a little wire that goes back to A. So here's what happens. So from A to B, for this battery, it says it's 1.5 volts. So for A to B, you gain 1.5 volts here. If you look at the voltage drop for each of the devices in this circuit, if I add all of them up, it's going to correspond to 1.5 volts. So it gains 1.5 volts across the battery, and it's going to drop 1.5 volts to the end. So that's always true in this nice little circuit here, is that you're going to see the voltage drop add up. You will notice that when we do labs, you've seen that we have some different kinds of batteries or different kinds of light bulbs. Some of them are round, some of them are bigger and round, and some of them are kind of what they call a long bulb. They're kind of tall. Each of those have a different voltage rating on them, and if you use two different ones in a circuit like this, you would find two different voltage drops if you were to graph that voltage drop. So again, the reason for the voltage change across the bulb, I like how it says this, there's a pileup of charge. So I'll talk about light bulbs a little bit more in one of the next videos, but that's what happens with the light bulb, is that the current goes into the light bulb up, and then it's pushed across this filament. And if you've ever looked inside an incandescent light bulb, the filaments are very, very small, and that's on purpose, and that's what causes them to give off light. So but that does create this pileup of charge, and that's where you get the voltage drop. So, and I mentioned that last one, that different bulbs give you different voltage drops. Okay, the role of a battery. So I kind of mentioned this already, but what a battery does then is that a battery takes chemicals, and through a chemical reaction it transforms it gives you an electric potential. It gives you that electric potential energy, and then you can use that in the battery for current. So basically, if you think about this as kind of a regular analogy to something like a common thing for circuits is to use like a water pump as an analogy. If you use a water pump as the analogy, this would actually be, the battery would be the pump, the water would be the current. Okay, the slope of the pipes would be the voltage, and we'll talk more about some of those analogies as we go. So that's the role of the battery, is to supply that electric potential energy to start with. Okay, so as far as energy goes, you start again at the high potential, like we saw in our diagram, and then the current is going to go through each one. Now, depending on what you have in a circuit, you might have a motor or a light bulb or whatever you might have in there, a toaster. The energy then is going to do something. It's going to do work. In a light bulb, it's going to make light. In a motor, it's going to cause it to turn, that sort of thing. So as it does that, it's going to, I wouldn't say use up that energy, because the energy is still there, right? Law of conservation of energy, but to transform it into something else. So into light, into heat, into motion, whatever you're trying to do with that. So if you're talking about a positive test charge, it's going to go all the way through the circuit, ends up back at that negative terminal, and then if your battery is good, that battery will pump it back up to the positive terminal, and it'll just repeat the cycle over and over again. So a couple things for an electric circuit, and this is our last thing here, is that, so what is an electric circuit then? By definition, it's just a closed loop that charges can move through continuously, and completing the thing that I just said on the last slide. So there's two things you really have to have an electric circuit. You have to have a closed conducting path. And you guys saw that when you did the little lab with the light bulbs and stuff, that if you don't have everything touching exactly right, if your path isn't closed, then you're not going to be able to light up your light bulb. So that's all that's saying. You have to have a path that goes all the way around. The other thing is that there has to be an electric potential difference between the two ends of the circuit. What that means is your battery can't be dead. So eventually, if you're talking about like a regular, cell battery that you use in electronics and such, eventually that chemical reaction will be done, will finish, and there won't be enough stuff to keep making an electric potential difference. So when that happens, then your battery's dead, and then you recharge it or recycle it or whatever. So that's all this video was, is just to kind of give an intro on electric circuits. We'll do all the stuff with resistance and voltage and current and all that stuff soon. All right, good stuff.